We begin the course with the unit on logic, which will lay foundations for the mathematical concepts and the way that we will prove and show things throughout the semester. Within the section itself, we're going to talk about propositions and various operations on logical propositions. We will then talk about logical form and logical equivalence in particular, which will allow us to prove that some statements are actually equivalent. We will then focus in a little bit on conditional statements. So those are the statements in the form if-then that are obviously used a lot in computer science as well as mathematical proofs. We will talk about what valid and invalid arguments are and how we can actually prove a theorem or a statement by using logical forms. As applications within this section, we're going to talk about digital logic circuits and number systems. So let's begin with a definition of what is a statement or a proposition. A statement or proposition is a declarative sentence that is true or false, but not both. So let's go through some examples to see if we can classify the following as propositions or not. So remember, it has to be a declarative sentence that has to have a value that is either true or false. 4 is greater than 7. Is a declarative sentence. It is false, but it is a declarative sentence that is false and certainly not true, so can be both. Therefore, it is in fact a proposition. She has a dog. It is a declarative sentence, but can we determine whether it's true or false? Well, it depends on who she is. If she is I, then yes, I have a dog. But if she is somebody else that doesn't have a pet dog, then that will be false. Therefore, for this particular sentence, we cannot decide whether it's true or false, which means that it is not, in fact, a proposition. 2 plus 3 equals 5. It's certainly a declarative sentence, and it's certainly, in the integer arithmetic, true, which makes this a proposition. I encourage you to pause here for a second, pause the video for a second, and go through the rest yourself, trying to figure out whether you believe that these are propositions or not, as per our definition, and then come back to the video to go through this together. Abbotsford is a city in Canada, indeed, a declarative sentence, and it is true, which makes this a proposition. X is bigger than 0 is actually a situation similar to she has a dog, because while that's a declarative sentence, the truth or false of it depends on the actual value of X. So that means that we cannot determine it right now, which means that this is not in fact a proposition. Where are you going? This one is not a declarative sentence, it's a question, so it fails to be a proposition just simply due to that reason. I live in Abbotsford and I like dogs. Well, it's a declarative sentence, but we actually notice that it's composed of 2 parts. The fact that I live in Abbotsford and the fact that I like dogs. Each one of these separately is a declarative sentence that is true or false. So this is a proposition and this is a proposition, but we don't quite know yet how to deal with the fact that it's kind of like 2 propositions glued together. This connection and is something we're going to have to discuss in a little bit more detail. If it is sunny tomorrow, then we will go for a hike. Again, this is a more complicated statement, and in fact of the conditional form that I mentioned earlier. So this is something that we're going to have to discuss in more detail about whether or not it's a proposition and what its true or false, truthfulness or falseness are. Now, you notice that already this is getting a little wordy. I would like to potentially be able to work with these propositions, so we're going to come up with a shorthand to refer to them. Normally, we use lowercase letters, and generally, we start with P for proposition. So for example, I can say that 4 is greater than 7 is proposition called P, whereas 2 plus 3 equals 5 is a proposition I will call Q, and then I can refer to them by their short name, P or Q. The truthfulness or falsity of the proposition, it's called its truth value, which we denote by true for T or F for false, or alternatively in computer science in particular, 1 for true and 0 for false. We will be using T and F throughout with dealing with propositions, and once we get into digital circuits, we will be switching to 1 and 0. However, if you're more comfortable with one over the other, by all means use the system that you actually prefer. Notice, looking at our examples back here, that some of the statements can be propositions, but will be false. So for example, 4 is greater than 7 is of course false, while 2 plus 3 is equal to 5 is true. Both are propositions, but they have different truth values. Let's take a look at this sentence. And we're asked to determine the truth value. So we're asked to decide whether it's actually true or it's false. The statement here is, this sentence is false. Well, how can we go about analyzing something like this? First, we can decide that there are, of course, two cases. Either this sentence is true or it is false. And we're going to split our analysis into two of these particular subcases. So if it's true, if this sentence here is true, then it says that it's false. So if we assume that the sentence is true, then it tells us that it's false. If, on the other hand, we assume that it's false, then the sentence itself saying it's false is false, which means that it is in fact true. This seems to be a problem. Whatever truth value we're assigned to it, the statement itself contradicts it. And this is what we actually call a paradox. A self-contradictory statement like that is not a proposition, but rather a paradox. So be careful when analyzing things for whether or not they're propositions. It has to be declarative, but it also has to have a truth value that is either true or false, cannot be both, and has to be able to be determinable. So the natural question arises after that is, do all propositions have known truth values? So notice that because we are talking about propositions, by our definition, it is a declarative sentence that is true or false. The question here is really about, do they have to have known truth values, so known to us? And the answer is, well, no, not necessarily. For example, things like conjectures or theorems that have not yet been proven, you can have a statement that you know will have a true or false truth value, but you might not yet know how to actually show that. So yes, this is absolutely possible to have propositions that have truth values that are not yet known to us. Now, going back through our example, you notice that while so far these definitions help us deal with these propositions and determining their truth values, we don't yet have ways to deal with the last two, and that is because they have a bit more of a complicated form. These are what we call compound statements. They are statements formed from two or more other statements by various operations. And in fact, we will think about the main 5 operations as the following. First of all is a negation. We denote it by a little bar in front. Some books refer to it as the bar on top, and some replace the little symbol with the tilde in front. The way we read this is not P. Again, remember that P refers to a particular proposition. So for example, P can be 4 is greater than 7. So then not P would be not 4 is greater than 7. Well, if you think about this for a second, this would mean that 4 is less than 7. You can already begin to think about what that means for the truth value of the proposition and its negation. If the original proposition was false, like the case with 4 is greater than 7, then not P will have truth value as true. It is a true negation, so the truth value also gets flipped. The second operation we're going to see all the time is what we call conjunction, and it's formed by a symbol like this. The way we read this is and. So this is P and Q. For the ease of simply remembering, I think of this symbol as sort of a beginning of writing the letter A without the little bar. So you can remember that this symbol corresponds to and, Whereas disjunction, the next symbol is the flipped little v, and that we read as or. So this is P or Q. We will talk about the actual truth values of them in a little bit, but again, getting a little bit ahead, think about what you normally in everyday colloquial English, what are the distinctions between and or that you can think of? If you're saying, I like ice cream and I like dogs versus I like ice cream or I like dogs, what are the cases where the distinctions actually are? The implication is what we form a conditional statement with, and so this we read as P implies Q, or we can read that as if P, then Q. The biconditional, notice that the arrow becomes two-directional. We will read as P if and only if Q. And we will go on to later prove that this actually does mean implication in both directions. So this statement means that P implies Q and Q implies P. Now that we have our operations, let's see how they actually work. So let's define the following statements. P will correspond to the statement, it rained today. Q will be, the ground is wet. And R is, I had lunch outside. So this is just to get used to the notation and also to turning logical operations into simple English statements. I urge you to pause the video here and try to write down sentences that correspond to each one of these logical compound statements by yourself first before going back into the video. So pause right now, come back in a minute. So what we have here is R and not P. And we can simply just read this off the actual definitions. R means I had lunch outside. And not P. So I have the statement, it rained today, and I have to negate it. And it didn't rain today. Sometimes it's easier to think of negation as, instead of actually already inputting the negation into the statement, you can say, it is not the case that it rained today. But with more practice, you should be able to simply actually inject the negation straight into the English statement. So what do we have for the next one? We have not Q, so the ground is not wet, or I had lunch outside. Now looking at the last one here, looks the most complicated, and you notice the use of the brackets. Now the brackets in logical statements are used exactly the same way as in regular arithmetic. You must obey the brackets when doing the order of operations. Whatever is in the brackets must be done first. So here we have our disjunction first, P or Q. So it rained today or the ground is wet implies not R. So implies that I did not have lunch outside. Again, notice that you can use the implies that statement, or you can use the if-then statement. If it rained today or the ground is wet, then I did not have lunch outside. Now, the second part of this exercise does exactly the opposite thing. We're going to start with the English statement, and we're going to try to turn it into a compound statement with the propositions that we defined. Again, I urge you to take a second here and try to do this by yourself before tuning into the video again for the answer key. It did not rain today, or the ground is not wet. So we have the proposition that defines it rained today, and there is a not here, so it's going to be not P. This first part is not P. Or is defined as a disjunction with a symbol like this. And the second part is the ground is not wet. We have the proposition that is corresponding to the ground is wet. That's Q. If it's not that, it means that it's a negation of Q. So we have not P. Similarly for the next one, we're going to match the statements that we have here to the ones we have defined and then see what operations we need to use to connect them. If it rained today, then the ground is wet. You immediately notice this construction, if then, which corresponds, of course, to the implication. It rained today corresponds to the proposition P, so I have P on this side, and the ground is wet corresponds to the proposition Q on the other side. So if P, then Q. This one is pretty straightforward. Let's take a look at a similar example where we just practice a little bit more of turning English statements into logical forms. Once again, I suggest that you pause the video here so that you can try this for yourself before we're going to go through this together. So the propositions that we have defined here is Amanda is healthy, and that's H, Amanda is wealthy, and that's W, and Amanda is wise, which is S. Let's see how we can do through all of these. Amanda is healthy, so that's H, and Amanda is wealthy, so that's W, but not wise, so not S. The interesting word here that we have not encountered before is but. So how are we going to deal with that? We don't have a connection for but. We have and, which is the conjunction. We have or, which is the disjunction, but we have nothing for but. Thinking about what but actually means, it's easy to persuade yourself that I can replace it with an and keep the same meaning. Amanda is healthy and wealthy and not wise. But is used for emphasis in English that what you have coming is maybe a little bit unexpected, but logically it's actually equivalent to and. So remember that but in terms of logic is the same as and. What we're going to have then is Amanda is healthy, which is H, and Amanda is wealthy, which is W, and Amanda is not wise, so not S. Going through the rest of them in a similar fashion, we will encounter some other words that we haven't seen before. Either Amanda is wealthy or wise. The trick here is to focus in on the or. Again, either is not really necessary. It's more of a grammatical construction in English. We can simply focus in on this part of the sentence. Amanda is wealthy or wise. So we have she is wealthy or she is wise. If Amanda is wealthy, she is not wise. There we have our if and then statement, except for notice that the then is omitted because, again, if the meaning in English is clear, then some words will actually get dropped. But this is an implication statement. If Amanda is wealthy, so W, then Amanda is not wise, so not S. Going through the rest will be very similar. Again, if you haven't paused the video and tried this for yourself, do it now. You can watch me do it 100 times over, but nothing will be as good as trying it for yourself first. Amanda is neither healthy, wealthy, nor wise. So now we have to think of this English construct and what does it actually mean? Neither nor. It means not healthy, not wealthy, and not wise. So we can just go through all of these with the negation. Not healthy and not wealthy and not wise. So again, the trick is to think about the actual meaning behind the statements, not necessarily the grammatical structures. Same grammatical structures will often correspond to, or rather different grammatical structures will often correspond to the same logical statements. For example, the but here is an and neither nor is an and with the negation all over the place. Amanda is neither wealthy nor wise, but she is healthy. So we have the neither nor statement here. So Amanda is not wealthy and not wise. And maybe I will put the brackets to indicate that this was the first part of a sentence. But she's healthy. We've already decided that but corresponds to and. So and she is healthy. We will later learn that if the same operation persists throughout, you don't actually need the brackets, much with like a plus. If you're adding numbers throughout, you don't need the brackets. Sometimes you need them for emphasis. But while we're still learning, brackets are a really good tool to overuse rather than underuse. More brackets are better than too few brackets. The next few are going to be a little bit more complicated. Either Amanda is wealthy or wise, but not both. Not both is something we don't have the logical construct for, so we'll actually have to decompose this statement into some that we're going to be able to write down. So what does it mean by not both? Let's say Amanda is wealthy. Then she has to be not wise because she can't be both. On the other hand, Amanda can be wise, but not wealthy at the same time, because again, she can't be both. So once we have it broken down like that, it becomes a little bit easier to write down. Then what do we have here? Amanda can be wealthy and not wise, or she is going to be not wealthy, but she's going to be wise. So notice that this ensures that only one of the things is true, but not both, right? In each one of these brackets, one is negated and one is stated in the positive, and they cannot be true both at the same time. So what do we have for the next one? She's wealthy, but not both healthy and wise. Similarly to above, now we just have to deal with the three different propositions here. So we have that we can have Amanda is wealthy and healthy, but she can't be both healthy and wise. So in this case, she's going to be not wise. Or we can have the case where she is wealthy and not healthy, but then she can be wise. Okay? So the not both healthy and wise now refers to this substructure that is similar to the example before. Right? So in both of these cases, we have only one or the other, but we have wealthy for both of them because we're told that she's wealthy regardless. The only way Amanda is healthy is if she is wealthy. This one is tricky because we see the if here, so the natural inclination is to say that what comes after the if is going to be your first part. So this is, for example, wealthy. If wealthy, then healthy. But it's going to be wrong here, and it's going to be wrong because of this substructure. The only way changes the meaning of the statement. Notice that if we say wealthy, then healthy, it means that if she is wealthy, then she's certainly healthy. But this statement is different. It doesn't guarantee that she is healthy just because she's wealthy. It's saying that the only way possible that she's healthy is that if she is in fact wealthy. We're going to come back to this structure later. For now, I'm going to leave the answer here and ask you to ponder it before we explore it in more detail later when we talk about conditional statements. Can you persuade yourself that the answer to this statement is actually if H, then W? Let's recap a little bit what we have talked about so far. We defined a statement or proposition as a declarative sentence that is true or false, but not both. We then talked about compound statements and the operations that we can use to put together two simple statements in a more complex and complicated format. We then practiced going from the logical statements to their English equivalents and the other way around. What we have not yet talked about is what are the truth values of these more compound statements. So if I tell you that it didn't indeed rain today, what does that mean for the more complex statements that involve P? So this is going to be the focus of the discussion starting today. First of all, we need to come up with a way to somehow organize this information, and that way will be what we call a truth table. The truth table gives the truth values of a statement for all possible combination of its components. So the way that we make our very first truth table here is we start with two columns that correspond to the simple statements P and Q. We then are going to follow up with 5 columns that correspond to the 5 operations we have defined. For the statements that are the components of everything else, we will come up with all possible combinations of the truth values. So let's fill in the first 2 columns here first. Let's think about what are the possible choices. If P is true, then Q can be true or Q can be false. If P is false, Q can be true or Q can be false. And those seem to be the only options. With that at hand, let's fill that out. So I have true, true, and then P can stay true, but now Q has to become false. And then I have false, true, and false, false. The other way of thinking of how we can fill this out is notice that P sort of splits between true and false, and Q alternates on each entry. Okay, for two variables, for two of the simple statement, you will have 4 combinations of all the past possible values. Again, if you're more comfortable with the ones and zeros, there will be 1, 1, 1, 0, 0, 1, 0, 0. Now, the way to fill out the truth table is to proceed throughout the actual truth table. We will have that each row corresponds to the chosen truth values for the small components. So this entire row will correspond to P being true and Q being true. Whereas, for example, this entire row will correspond to P being false and Q being true. Now, you can fill out the table row by row, but it's actually easier to go in terms of the operation. So, for example, let's take a look at not P. Remember that not P is sort of the reverse of P. So for every value of P, not P will simply flip it. So what do I have in the first entry here? P is true, so not P here must be false. So I'll have to fill that out. What about the next one? Again, I look for the corresponding entry in the P column. It's true, so not P must be false. P is false here, which means that not P must be true. And P is false here again, so that means that not P must be true again. This one is a little bit different than the others because it only involves one variable, P. So in that sense, when I am constructing this column, the column for Q just gets ignored because it's not the part of this operation. For the rest of them, the operation will involve both P and Q, so we will be a little bit more comprehensive. So what do we have? P and Q. Thinking about how we use the and in colloquial English will give us some intuition about how we define it in logic as well. P and Q is defined to be true when both P and Q are true. That's the only case when it's going to be true, and it's going to be false otherwise. So P and Q, let me repeat this, is only true when P and Q are both true. So let's go row by row. So in the first row, I have true and true. They're both true, so the conjunction or the and is true as well. In the next row, I have true and false. One of them is false, so the conjunction is false as well. The next row, I have false and true. One of them is false, so the conjunction is false. And the last case here, I have false and false. Well, they're both false, so the conjunction is false. So notice that this and column is kind of not very forgiving. It's only true if both of the values are true, and it's false for all of the other cases. In case of an or, we're going to see a much more forgiving situation in terms of being true. Or is true if at least one of the components is true. Okay, at least one. So let's go through. True or true in this row? Well, at least one of them. In fact, both of them are true, so the disjunction is going to be true. The next one, we have true or false. Well, at least one of them is true, so or will be true. False or true, again, at least one of them is true, so we're going to have true. False or false, well, there isn't one that's true, so that means that in this case, it's going to be false. Okay, so looking at this column now, notice that the or is only false when both parts are false and is true otherwise. It's not quite the opposite of and, but it somehow has a little bit of the contradictory feeling, right? So the and is very unforgiving in terms of true. It's only true if both P and Q are true, whereas or is only false the one time when both of the components are false. The implication P implies Q is only false when it's truth implying false. Let me write this down, in fact. So P implies Q is false only when we have truth implying false. And we will investigate that in a second. But for now, I'm just going to fill out the truth table that corresponds to this rule. So it's only false when truth implies false. So true implies true. That's not one of those cases, so it's going to be true. True implies false is exactly this case. So my entry in the table here will be false. And then I have false implies true, which is not. True implies false, so this is going to be true. And the last case of false implies false also doesn't fall into this category here, so it's going to be true. Okay, so again, looking at the column, we're going to reconfirm that we filled it out correctly. It's only false when we have true implies false, and it's true in all the other cases. In fact, often when I construct truth tables and it involves the conditional, I will put in the falses right away and then fill the rest of them with truths that don't correspond to the true implies false. Again, we'll come back to that in a second to explain the actual intuition behind this. The biconditional is essentially the logical equality. So the biconditional is going to be true when P and Q have the exact same truth value. So either they're both true or they're both false. So here I have true and true. So the biconditional, again, the logical equality will give us true because they are in fact the same. The next one is true and false. Well, they're not the same, so the biconditional will be false. False and true, again, not the same, so the biconditional will be false. And then false and false, well, they are the same, so the biconditional will be true. Okay? This truth table defines the basics of all the truth tables that we're going to deal with later on. So go through that, make sure you sort of internalize these rules as the negation that flips everything, the and or the conjunction that is only true when both of the components are true, the disjunction or the or that's only false when both parts are false, the conditional that is only false if we have truth implying false, and the biconditional or the logical equality that is true in the cases where P is the same truth value as Q. So now, why are the truth values of P and Q defined in this odd way? It seems anti-intuitive, for example, that false implying true is somehow still true. If we have a false beginning and a true conclusion, how can the entire statement be true? And it's best understood maybe in terms of an example. So let's consider a promise that I'm going to make to you. And it's going to be fairly straightforward. If it's sunny today, then we will go to the beach. So in this case, P is it being sunny today, and Q corresponds to us going to the beach. We're going to go through this promise and this example and see how the four different values for P and Q affect the truthness of the entire statement. So suppose it is sunny today and we went to the beach. That means that we started with the truth, it was sunny, and we went to the beach. That means that I kept my promise. If it's sunny today, I actually committed to going to the beach, and we went to the beach. So this corresponds to truth value as the value for the entire statement, that if it's sunny today, they will go to the beach. Okay, this is our first row in the table. The next one is true implies false. So in our case here, that means that it was sunny today, but we did not go to the beach. Well, this case is problematic because I promised that if it was sunny today and then we'll go to the beach, it was sunny, but we didn't go to the beach. So I made a promise and I broke it. And that is what corresponds to the false value of the conditional, a broken promise. The premise, which is the first part of the conditional, was true, but the conclusion never happened. The next case in the table is false, implying true. So it wasn't sunny today, but we went to the beach anyway. Did I break my promise? It wasn't sunny today, so my promise didn't even apply. Plus, we made it to the beach anyway. So my promise didn't get affected, which means that my promise is, by default, still held. And finally, the last case is, it wasn't sunny today, and we didn't go to the beach. Again, in terms of my promise, it doesn't matter because it wasn't sunny in the first place, so that did not affect the original statement at all, which means that I never broke my promise, and this is still true. So this is why the conditional statement is only false in the one case, when we started with a truth and the conclusion was false. The case of a broken promise is the only case when the conditional is false. All the other cases are actually true. These last two cases, when we start with the false statement, means the promise doesn't even apply. So these two are called vacuously true because they are true by default. My promise isn't even relevant to these cases, so no matter what happens, the overall conditional will be true. Now, with this in mind and with these values for the truth values of all the operations we defined, let's go through and fill in this truth table so we can practice a little bit more of both how to fill in the truth table, but also what to do with more complicated operations that appear in the truth table. I encourage you to take a minute here and actually try this for yourself before proceeding with the video. Okay? Again, practice is what you have to do with these types of very technical things, so it's much better to try it for yourself first. So I already have the pre-filled columns for P and Q. The first column out here that I'm going to have is not P. And just like in my table up here, what I'm going to have to do is simply negate the entire column of P one row at a time. So here is the negation of truth, which is false. The next one, P is true, so not P is false. The next one is P is false, so not P is true. And the next one is again P is false, so not P is true. This column is not Q, so I have to negate this column. Notice that the label or the truth values are not the same, so don't just copy it over because it's negation and this is negation. That's not going to work like that. They are in different order row-wise, so you really have to look back at the column for Q and fill it out correspondingly. So true here for Q means false for not Q. False here means truth here, and so on. So I'm going to have false, true, false, true. Excellent. And proceeding in this manner, we're going to look at the other columns. Next up is P and Q. So remember, and is only true if both of the values are true. So it's only going to be true in this first row and false everywhere else. Now, it's going to take a little bit of time and practice to actually get fast at filling truth tables, and you're never going to get quite fast enough, it seems, or efficient enough, because the truth tables by design are big and detailed. So, but going through the operations and getting familiarity with them will certainly speed up the process. Now, this next one up, we have to be careful about the brackets. So it's not, here it's denoted by the tilde, not the little bar, so be careful about that. But it's not of the P and Q. So it's the negation of this column. And that is important. There is no way that we know of yet how to open up the brackets with a negation, so don't. Obey the brackets. First, we're going to do what's inside the brackets, which is P and Q, which corresponds to this column here. And then we have to negate this column. So all we have to do are negate these four values as they appear. Okay? So once again, this P and Q is this column here, which means that the negation of it will simply be the negation of this column. So negated truth is false, negated false is true, negated false is true, and negated false is true. And here we have completed our first column that involves brackets and multiple operations. Notice that everything in our basic truth table here involves only one operation per actual heading, whereas here we're getting into a little bit of the weeds with multiple operations. The next one is going to be in a similar vein. We have not P and not Q. So my connective here is the and, but it doesn't connect P and Q. It connects not P and not Q. So now I have to look at the corresponding columns here. Not P is my column here. Not Q is my column right here. And I have to connect these with an and. Remember that the and is only true when both of the components are true. So let's go through this carefully. I have not P and not Q. So false and false. That's going to be false. The next one, false and true, is going to be still false, because in order to be true, and has to have both components be true. The next one up is true and false. Still not both of them are true, so still false. And the last one is true and true. Both are true, so we actually have a true here. Okay, let that sink in for a second and think about the process again. In order for us to fill in not P and not Q, we had to look at the column for not P, and then we had to look at the column for not Q and connect them with the conjunctions. So this column and this column, and we filled it out one row at a time. Okay? With that in mind, if you haven't paused the video and tried it for yourself yet, stop here and try the rest of the columns by yourself. It's going to be a very similar procedure, but with the or as the operation. So, carrying on with an or, here I have P or Q, so I'm back to my original two columns. True or true is going to be true. The next one is true or false, still true. False or true, still true. False or false is false. Remember that in order for or to be false, both of the components have to be false. The next one up is not P or Q. So just like in the case of or, I am going to be negating this previous column that I've just constructed. So P or Q is this component, which means this column, and I am negating all of those truth values. So true turns into false, and then true turns into false again, true turns into false, and for false turns into true. The next column is similar to the one that we've dealt with an and, where I have to look at the columns that correspond to not P and the column that corresponds to not Q, and I have to connect them with an or as the compound statement is formed. So I'm going to see and go through row by row. False or false. Remember, or is going to be true if one of the components is true, which is not the case here. So my first value here is false. Next, I have false or true. Well, one of them is true, so the entire statement is going to be true. I have true or false. Again, one of them is true, so I have true. And for the final one, I have true or true, which results in the truth. Okay? Again, pay close attention. I'm looking at the corresponding columns and connecting them with the prescribed operation. The next up is the simple P implies Q. So in a sense, I can just copy over this column as long as the variables are listed in the same order. Or, as I mentioned earlier, what I normally do for the implication is find out the cases where it's false. I know that it's false in the case of a broken promise when true is followed by false. So this is only going to be false when I have truth implying false, which is in this case right here. So in my second row, I will have false, and I will have truths everywhere else. Excellent. Next up is the negation of the implication. So it's the negation of the previous column, just like we've seen before in those cases, all I have to do is negate the column that came before. So I'm going to have false, true, false, false. Excellent. And the last column in this practice truth table, not P or Q. So just like we've done before, I'm going to have to look at the column for not P, and then I have to look at the column for Q. And I'm going to have to connect the two of them with the operation of OR. So not P, false, or Q, which is true. False or true is still true, because remember, OR is only false when both of them are false. Next up is false or false is false. The next one is true or true, so that's true. And finally, the last one is true or false, which is once again true. Okay? And this is how you fill out a truth table. In terms of complicated expressions, we will see more examples later, but this is essentially what you have to do. If you are given, for example, an expression like this to construct a truth table for, you're first going to construct a column that contains P and Q. So you're going to have this as a sort of additional or supplementary or, helpful column, though not your final column. And then you're going to have a negation of that. So we're going to have to break up more complicated statements into components and construct columns for each of these additional supplementary ones. But just looking at this truth table overall, if you stare at it long enough, you can't help but notice some interesting patterns. For example, I can see that this column in its truth values is the exact same as this column. I have false followed by all truths. Does that mean anything? Is that useful somehow? I can also notice that, for example, these two columns are also the same. So here we have true falses, all followed by one truth. Maybe that means something. And then finally, I can notice one more equivalence in these columns, which is these two. This will actually turn out to be quite a useful thing that we will come back to later, which will also prove yet another use for the truth tables. Let's take a look at another example here in terms of not quite the truth table, but evaluating the expressions for specific values that are given to our variables. Okay, so what we have here is A is 3, B is 5, and C is 6, and we have all of these different propositions to consider. Let's take a look and see if we can decide whether each one of them is true or not. So the first thing we can do is replace A, B, and C by the corresponding numbers. So in this case, we have A is 3 and B is 5. So we have 3 is greater than 5, and then we have not in front of it. Okay, so let's pause at this and here and only think of this sort of left-hand side so far. 3 is greater than 5. Is that true or false? Well, we know that that is, in fact, false. 3 is not greater than 5, so it has a false as a truth value. But then there's a not in front of it, right? Not false is, of course, true. Okay, that's for this part of our statement. What about the second part? So here we have B is less than C. B is 5, C is 6. So is it the case that 5 is less than 6? Yes, absolutely. 5 is in fact less than 6. So the truth value here is true. And so what we have overall is putting everything together. Remember that there's an and in the middle here. So what we have is true and true. And we know that for the and, the only time it's true is when both of the things are true. So the overall conclusion here is that that statement has the truth value as true. Okay? This kind of logic sometimes will take a little bit longer to figure out because you have to go through separate parts and you have to submit everything, and then you have to apply the rules that we've already seen, but just as long as you're consistent and doing one step at a time, there should be no problem. I'm going to leave this one as extra practice, but I'm going to do one of the implications. So let's take a look at this one. A is less than B. So what do I have here is 3 is less than 5. And this implies that A plus C, so 3 plus 6, so 9 is less than B plus C. So 5 plus 6, 11. Okay? Is that a truth statement? Well, let's take a look. 3 is less than 5. Yes, that's true. And this implies that 9 is less than 11. Is 9 less than 11? Yes, 9 is in fact less than 11, so this is also true. And now we have to take a look at this statement. What is the truth value of an implication that goes true implies true? Well, we can take a look at our handy-dandy truth table here. In the implication case, when true implies true, we have true. So the overall truth value here is also true. Okay, so be careful. Just because you're seeing things like true everywhere doesn't actually mean that the final result will be true. You really have to once again consult the truth table or how the actual operation of implication works. It's also important to remember here that because it's true for this particular choice of values, it doesn't mean that this proposition will always be true. It's only true for A equals 3, B equals 5, and C equals 6. If those numbers get changed, we might actually get a different result here. Okay, I'm going to leave the other two to you to practice. Again, following the same logic, plug in the numbers, and then follow the operations to determine their truth values.